All right, welcome to this talk about secure coding back to basics. So this is a talk that I've been wanting to do for quite some time, and it came out of thinking about how we write our code. I've been going to a lot of conferences, been in a lot of conference committees and seeing talks that are about how to make your application bulletproof using some kind of thing, where that thing is usually some kind of security thing like an authentication solution or something like that. And while that thing might be perfect in solving that specific thing around security, it might not be something that secures the entire application. There might be other problems in there as well. And often we fail on the basic stuff, like how we write our code, like the basics of code writing. So that's what this talk is about, like how we write our code and how we can do that to make our code more secure than it would normally be. So I'm Alan. I've worked as a software developer, pen tester, security architect, and all kinds of stuff for over 20 years. I'm now a security researcher at a company called Crosspoint Labs. I also build open source security tooling, where Retire.js is the most famous one. And I'm the chapter lead for the OWASP Oslo chapter. Complexity is the enemy of security is a quote that has been uttered by many different people, most famously probably Bruce Schneier, who talked about this a lot, how if we make our systems more complex, that makes them harder to secure. And this makes a lot of sense, right? If we have a system that's complex, that's hard to understand the code, we allow vulnerabilities to creep in because we have to understand the code to be able to secure it and find the vulnerabilities in the code that we're writing. And the code that we write and the systems that we create, they rarely start out as complex. They might be something easy at the beginning, but as we add more features, as we add more stuff to them, they become more complex, especially if we forget to clean up stuff, we forget to remove things that are no longer used. And in fact, a Standish Group study it's a few years old now, but it said that 45% of features in a typical systems are never used and 19% are rarely used. So over half of the code that we have is basically laying dormant and never used. So we need to be better at cleaning up stuff, and that would also help us reduce the complexity. So we need to take down the technical debt. If we don't do that, or if we don't pay attention to the code we write, we will get vulnerabilities. Vulnerabilities are just bugs like any other bugs. But they tend to be treated differently in many companies, like there's a certain amount of secrecy around them, not everyone gets to know about them. But I think we should try to just bring them into the normal backlog, handle them as normal bugs, and then get them done and learn from them, just like any other type of bug. 50% of these vulnerabilities are business logic bugs, which means that they are a type of bug that cannot easily be found by a security tool because they are about how our application works. So one example of this could be, let's say it was an expense system where you can register your expenses and get paid back by the company. Maybe you should not be allowed to approve your own expenses because that would create like a problem. That's not something a security tool can know because that's just a business rule, but it can be seen as a security problem if you can kind of approve your own expenses and then like extract money from the company. So that's just one simple example. Now, bugs, I have a personal preference for bugs. I really like compile time errors because they're in my face immediately. I fix them and they never go into production. So if I can make things compile time errors, that's great. Next one is something that's caught by automated tests, because again, it doesn't reach production, it doesn't fail for the customers. It's something that I will see and I'll fix it. Next one is if I'm doing pull requests and someone is reviewing my code and they're saying, hey, this thing doesn't look great, please fix it. Again, that's better than having it into production. And even stuff that's caught by manual testing before going into production. If someone's testing things and oh, this doesn't look right, and then they tell me, at least it's found, hopefully, before the code goes to the customers. And then runtime bug in production. Those can be quite bad. But even worse if it's a vulnerability, and even worse than that if it's an exploited vulnerability. So meaning that someone on the internet has found this thing and used it to attack me. hopefully it's then a nice person that would just report it to me and tell me, hey, I found this thing, please fix it. But it could also be someone hacking my stuff and then removing everything. And last but not least, those runtime bugs that only occur at certain times that are super hard to debug and you can never find them again, and they happen once because there's some thing in the log about them, but you don't really know where they are, and you spend weeks trying to figure out what happened. They could also be vulnerabilities, but they could also just be a normal bug. So the point of this is I want to push anything that happens, like vulnerabilities or bugs, I want to push them upwards. So I want to make them into something that I can find as early as possible. Shift left, if you will. I want to make things compile time errors if I can, so I don't do something stupid. So in 2006, I wrote this blog post, and I don't expect you to read this, no worries. It's just, you can read the title of it, Why Input Validation is Not the Solution for Avoiding SQL Injection and Cross-Site Scripting. And I wrote this in 2006. And a couple of years later, there were some guys from Sweden, Dan Berg-Jonsson from Omega Point and John Wilander, who also worked at Omega Point at the time. They were playing with this idea of something called domain-driven security. And they had read some of my blog posts and asked me to kind of join in and help them work this thing out. And the idea of domain-driven security, it takes inspiration from domain-driven design. So we're going to take like concepts and things from domain-driven design and see how we can use those to get better security in our code. Some years later, Dan Berg-Jonsson and a couple of other Dans, they wrote this book called Secure by Design, which I helped review, and it's a super good book. I don't get paid to say this. I just like the book. I think they did an awesome job at writing that book. So I highly recommend you read this book if you like what I'm talking about today. Some terminology that we're borrowing from domain-driven design is ubiquitous language, which basically means the language that we're using inside of a company that has a specific meaning within maybe the company or maybe a department within the company. And I'll show you an example in just a second. But it's a specific language. We're using words in a specific way where they mean something different than they might mean in our like normal community. And these languages we typically use inside of something we call a bounded context, which is basically where this language is valid. So this could be, again, it could be a department, it could be an application, it could be a microservice even. And at the edges of this, we have an anti-corruption layer to make sure that we translate from what this means on the outside to what it means on the inside and stop things from coming in that don't make sense. So as an example, maybe we have a sales department, and the sales department, where we are in a web shop and we're selling books. So we want to sell something, and the word quantity in this case means something that's larger than 0 and smaller than 200, because we don't want to sell like big chunks of books, and we can't sell 0 books or -1 book. That doesn't make sense. But maybe if we go to the returns department, they have a different definition of the word quantity, because there they can get returns, so you can actually get -1 book, because that means someone returned the book. And this is interesting because you can see where this could fail in a web shop if we allow negative numbers, and this has happened. So a company I worked at, they ordered -5 TVs, and they actually got the TVs delivered, and it was only discovered because the company that sent them the TVs were also wondering why they owe them money. Because in one system it looked like they have returned 5 TVs, and the other system it looked like they should send them 5 TVs. So this can happen. And when we think about what's going on here, we have these concepts that are that we're moving across. And if we look at a very generic drawing of an application, we can have a database. It could be a SQL database, it could be an SQL database, it could be just like a Redis or whatever. It doesn't really matter for this. We have some kind of query language, which could be SQL, but it could also be some other type of query language. We have some server-side code. It could be Java, it could be TypeScript, it could be C#, it could be Go. Then we're transferring something over to JSON to get it into the browser, where there's some JavaScript running that's using some kind of templating to make this into HTML. Now, In this diagram, the same piece of data, the same entity, will have many different representations. So think about a user account, for instance. So a user account can be a row in a database table, which is then sometimes a part of a query, which then becomes a server-side object called user, maybe. Sometimes it goes over to JSON to go over to the client side, handled by JavaScript, goes into multiple templates, and has multiple representations in the UI. So in the UI, it could be like the avatar up in the corner showing that you're logged in, but it could also be the profile editing form. It could just be your name somewhere where you've edited a blog post or something. So the same thing has many, many different representations within this diagram. And the reason why I'm bringing this up is a lot of the security vulnerabilities we get are when we go from one representation of something to another. So when we go from server-side to SQL, this is where SQL injection occurs. When we go from a JavaScript and a template into HTML, that's where typically cross-site scripting occurs. So when we transform between all these different types of representations, that's where most of the vulnerabilities come in. So we're going to start with input validation because it's something that when you ask security people, what should I do with this application? Well, you should add input validation. You should validate your inputs, or sanitize your inputs, is something they'll say. So I actually think that the goal of input validation is not necessarily security related. It's more about data quality. So ensuring that data is on the right format. So think about the quantity. We want orders that have a quantity that makes sense. That's not like -2 million or something. So it's a data quality thing. But as we get good data quality, that also stops and limits many types of attacks. So it's a nice side effect, but it's more about data quality than it is about security, but that's a super nice side effect. So how do we do this? We have different things that we have to look at when thinking about input validation. So first, syntax. Is this on the correct format? So if it's supposed to be a date, does it look like a date, or does it look like a large blob of random gibberish? Then semantics, does this value make sense in the context? And I'll show you an example in just a second. But is this a sensible value in our application? You can again think about the quantity, like is this within the bounds, or is it just like a random number that's super high or super low? And last but not least, is this something that makes sense according to the rest of our application, the data that we have in the database? So if it's a product ID, does it exist in our database? Or is it just like a random idea that someone made up? So these three things, syntax, semantics, and domain, people will call them different things. The main point of this is just to explain that we have to look at all of these three. But you'll find different names for them in different literature. But an example here for syntax for a birth date, we could check that. So this is a regex checking that we have first 4 numbers, then a dash, then 2 numbers, then a dash, and then 2 more numbers, and then we end the string. But this would allow a lot of different things. This would allow year 9999 and year 0 and all kinds of stuff, which we probably don't want. It would even allow month 99, which also doesn't make sense. So we can add some semantics as well. We check the syntax first. Does it look like a date? Kind of. Yes, it kind of looks like a date. Okay, let's check that we can parse it, and let's check that it makes sense within the context. So in this case, we probably don't expect to have users that are born earlier than 1900, and maybe we don't expect to have users that are born in the future at this point. So. Another example, validating a product ID. I already mentioned this. Maybe it's a number. Maybe it's just like an easy number, not like a complex sort of thing. So we check that it's numeric, first of all, and then we check that this is a product that we actually have in our database. So it's not like a random product. And then it gets more complex. So we have, let's say we're implementing a new version of Stack Overflow or something like that. So we want to check text. And free text from users is super hard to validate. So in this case, thank you for this blog post. Okay, we can start like adding some kind of regex for it. But it's quickly going to get complex once you start allowing users to discuss programming or even attacks, because then you're going to need to allow these attack strings to get in. And this is where you see like input validation starting to fail. as I mentioned in this blog post that I showed you. And this is still a legitimate comment. There's not something wrong with that comment per se. It's just how our system handles that comment that might be a problem. Another problem is often that we tend to check something and then we use it later, and sometimes we check the data in one place and then we kind of do something with the data while we're checking it, but then we use the original value later. So we're not actually using the stuff that we checked. So we might end up checking something over here and then using a different interpretation of the same data when we're actually using the data. So we've done a validation, but the validated data is not what we actually end up using. And one example where this often can be a problem is with character sets. So there was a Belgian guy called Matthias Beinens who did an excellent talk about this a couple of years ago. And he kind of explained this in a very good way for me. I hadn't really thought about how that actually works earlier. So if we think about Unicode, Unicode is a massive list of symbols, and there's all kinds of letters from all kinds of different countries and all kinds of weird symbols in there. And so Unicode is the list of symbols, and then we have UTF-8, UTF-16, and UTF-32 that are encodings of Unicode. In Norway and many other European countries, it has been common to use a different type of encoding called ISO 8859-1. And this one often, it only uses 1 byte per character, while UTF-8 can use from 1 to 4. UTF-16 always uses 2 bytes or 4 bytes, and then UTF-32 always uses 4 bytes for each character. So what's nice with UTF-8 is it's compatible with ASCII for like the normal English alphabet, but then it becomes somewhat problematic if we go into the more specific letters that are in certain languages. So in the Scandinavian countries, we have these weird letters A, Ö, O, which are not in the English alphabet. And they are 1 byte in ISO 8859-1, but they're 2 bytes in UTF-8. So if we look at the bits, it would look something like this in ISO. And then if we wanted to translate that into UTF-8, we have to know how UTF-8 works. So if the first bit is a 0, it means that this is a 1 byte character. If the first one is a 1, and then the second one is a 1, that means it's 2 bytes. And then if there's 3 ones, then means it's 3 bytes, and 4 ones, it means it's 4 bytes. So this this Norwegian letter would look something like this in UTF-8. And then if you try to interpret it the wrong way, it would end up becoming 2 letters, like this A with a curly on top and then this small little thing at the bottom. And this is what we often see in software that's interpreting character sets wrong. They do things in a weird way or end up with weird results. And here's another example that was used to hack IE back in the day. So this character here that's I don't know if it's Chinese or where it's from, but it's if you look at the bytes that's behind it, it's going to be 4 different bytes, where one of them is actually going to be the less than sign that you would use to start a script tag. And if you interpret this the wrong way, if you get this as UTF-32 and you send this in and it looks like something else, and then when you interpret it, it gets like 0 byte, this thing, and then 0 byte, that led to cross-site scripting basically, because the browser would ignore the 0 bytes and just use this less than character instead. But this is the more complex view of it. Let's go to a place where we can see this in action. So JavaScript, always fun to heckle a bit with JavaScript. So abc.length, a string, simple string with 3 letters. Of course, it has a length of 3. Makes sense. And then we add this double equal sign thing, and then the length suddenly becomes 4. Okay, that's a bit odd. Then we have an A with an accent equals an A with an accent is false. Okay, that's a bit unexpected. But one of them has a length of 2, and the other one has a length of 1. Okay, because one of them is the character A with an accent, and the other one is the character A and the combining character with an accent. So we can actually create an A with lots of these accents on top of each other. It looks something like this, and you can see it kind of breaks into the text above. And then we have this kind of family emoji, which has a length of 11. It looks like one character, has a length of 11. But to make it even more fun, let's look at this thing. So this is a spaceman emoji. and it has a length of 5. Okay, still looks like one character. If we do split on an empty string, so we take a string that has one character and we split on the empty string, we actually get 5 characters back. So yeah, makes sense. Length 5, we get 5 characters back. And here we can actually see how JavaScript handles these characters. It handles these characters as something called surrogate pairs. So the UTF-8 or the Unicode characters are basically represented by two different pairs with a combining character in the middle. So if instead of splitting on the empty string, we split on the combining character in the middle, we get this, a man and a rocket, which makes sense, a spaceman. It's a man and a rocket, and we combine them, we get Rocket Man, right? That's just how it works, and it's really, really funny how that turns out. And you can, the same thing, if you did the same split with a family, you would get like man, woman, child, or something like that. So why is this important for security? Well, you can imagine already that this is problematic for applications that try to parse the length of strings, where one interprets this as a length 1 and one interprets this as a length 5. But there's another example, and that's when we use the database called MySQL. Because if we try to create a table and we say, I want this table to have UTF-8, support UTF-8, it only supports up to 3 byte characters, not 4 as UTF-8 mandates, which is really strange. So if we store ABC and try to read it back, we'll get ABC. If we do 2 byte characters, we'll get them back. But sometimes if we add a 4 byte character like this double equal sign with these 2 on top of each other, sometimes that will just fail. In some programming languages, they will just get an error back from the database saying, I can store this, but they will just ignore it. And so we store something and we get something different back. So we can actually fix this in MySQL by saying the table should be UTF-8 multi-byte 4. But I don't know why they made those things different. But why is this important for security? Well, let's go back to Matthias. So he figured out there was a way to hack into Facebook's source code solution. Because the check that they had implemented was that if you're going to get an account with us, you have to have an email ending at @fb.com. But what he sent in was evil@hacker.com, pile of poo emoji, and then @fb.com. And the pile of poo emoji is also a 4 byte character. So what happened was it was sent to the server. The server says, yes, this ends in @fb.com. I'm going to store it in the database. And then the database just dropped everything starting from the pile of poo emoji. So it ended up with evil@hacker.com in the database. So what do we do about this? Well, we should always specify the character set if we can. So if it's an HTML page, we say this is UTF-8. If it's an API of any kind, REST API, let's remember to say what API or what character set this API is using. So we can add it at the end of the content type. Say this is character set UTF-8. And we should, of course, test with these multi-byte 4 characters. And this, again, the pile of poo test, that's also Matthias's thing. He mentioned this in his blog post about this. So I've used this thing. It even has the nice Norwegian letters, A and Ö in there. So he's used this, and I've used this in tests, and I accidentally broke the system completely by creating a product with that name because it's failed and couldn't read the products back from the database. It didn't just cut stuff up. It just said, there's something wrong with the data in the database. I can't read it anymore. So the whole thing went down. Luckily, this was in test and not in production. Another problem is if we try to do deny listing. So deny listing is when instead of doing positive input validation, we're trying to block stuff, block bad stuff. So we have this IP here. This is an IP that's frequently used on cloud services. So if you are running on a cloud server and you want to get to what's called the metadata host, you're going to use this IP. And by accessing that IP, you can get keys and stuff that you can use to access other services. Also, as a hacker, if you can make the application visit this IP and return the response, you can get the keys to the servers. So it's something that you really don't want people to get access to. So this is a normal IP. This is the same IP, but with overflow. And many parsers would just like throw away the overflow, and so we end up with the same IP as above. Look, the first one looks like an IP, the second one looks a bit odd. And then there's a numeric IP without the dots at all. Again, it's the same IP. Here's a numeric IP with overflow. Here's a hexadecimal IP. Hexadecimal IP without the dots. Hexadecimal IP with overflow and without dots. An octal IP in the 8 system. And again, even with like more zeros and stuff just to make it worse. So all of these are the same IP if they're interpreted by certain languages or certain frameworks. And you can imagine then like trying to figure out which one is this. Is it really the same one? Did we block all of these? And we don't necessarily have to block all of these. It's probably not a good choice. What we should do first is something called normalization. So before we check the value, we should bring it down to a format that's common, that's known. So in this case, we should bring it back to the original IP, remove all the cruft and make sure we have a clean understanding of what this data is. Some other examples of normalizations could be in XML, we can have an empty tag, which can be either an open tag and then immediately followed by a closing tag, or it could just be a self-closing tag. In character sets, I mentioned UTF-8 and all that kind of stuff. There are different ways of doing this as well. I'm not going to go into what NFD, NFC, NFKD, and NFKC means, but these are all different interpretations within a language of how something works with the accent and combining character and all that stuff. And then, of course, if we have international letters in URLs and host names and stuff like that, then we might have to resort to something called Unicode to kind of convert it back down to ASCII and use it. But these are just some examples. Another principle is we should, as best as possible, try to avoid cleaning up stuff. If we get something that's invalid, we should just immediately say, no, I don't want this, and return that to the client and say, this data is invalid, I don't want it. Just a simple example here, if you try to clean this stuff up, I'm going to remove the script tag. This is a classic example from many different applications that try to be smart to remove cross-site scripting. So they would remove the script, the start script and the end script, and then they would actually just, it's like an onion, you peel off one layer and then there's a new one underneath. So it would be better in this case to just reject it and say, I don't want this data. It looks like you're trying to attack me. And just return bad request or something like that. So kind of wrapping this up, we want to normalize. Then we want to check the length first. And the reason why we check the length first is some attacks rely on lengthy data. So if we can already first say, is this the expected length, then we can avoid some of those attacks. This could be something like, for instance, a regular expression denial of service. That's harder to do if we already set a small length for the data. Then we check the format and syntax, and then eventually the semantics. And then we use the normalized validated value. As you saw with the IPs, we could have ended up using one of those hexadecimal weird stuff all the way to the bottom. But if we normalize stuff, that's the data we should use later. And then maybe further down in the code somewhere, we need to check if the product ID makes sense or something like that. An example of these things is from something called Heartbleed. And Heartbleed was a vulnerability that was in OpenSSL. So they introduced a new functionality in OpenSSL where you could check if a connection was still open. So you connect somewhere, you want to keep that connection open for some time to exchange data and to make sure, is this connection gone stale and is it closed by the other side? You could send some data and the other side would just echo that back to you to check if the connection was still alive. Now, they had a vulnerability in this Heartbeat functionality called Heartbleed. And the way that worked was you would say that you had sent, let's say, 100 bytes, but then you just sent one. And what the server would do is it would look at the message and say, okay, I'm going to send back 100 because you said you sent 100, and it would just read that data randomly from memory from the following where where the byte that you sent was. So you could actually end up leaking private keys and password and other stuff that was in the memory of the server at the time. So the easiest way to explain this to my mother would be to say it's like going to a store, you pay with a 50, and then you kind of try to convince the clerk that you paid with 200 to get more money back than you originally gave. That's kind of how this works. And we can imagine if we try to look at one of these messages, maybe on its own, each of these fields were valid, but the semantics of the whole message didn't make sense. So there's one field that said, I'm going to send you 100 bytes or maybe a kilobyte, and then the next one just had like 1 byte in it. So the semantics of the entire message didn't make sense. But now I talked a lot about input validation, but I mentioned domain-driven security, and I haven't really talked much about what that means. So let's bring that in. And I'm going to show you another fun example from, this was from OS X on a Mac. So they were supposed to show you a password hint if you had forgotten your password. Sorry for the language in this. I couldn't find an English version of this. But they were supposed to show you the password hint, but they accidentally showed you the password instead. So basically just flip 2 strings. Okay, which one I'm going to show? I'm going to show you the hint, and then they had a bug that showed the password instead, which kind of ruined the entire security of that feature, as you can imagine. So these strings we keep passing around, that can sometimes be an issue. And this is a speaker that frequently goes to different like domain-driven design conferences and developer conferences to talk about coding, and has a lot of opinions about coding. And he wrote this Twitter rant. Did I mention I hate string? I hate string. People who have the decency to refrain from using object will gladly use string with assumptions all over the place. I really like this concept of string with assumptions, because that's something that we keep using all the time without thinking about it. And there's another blog post as well from the Secret Squad, and the blog post is called Something Isn't Something Else. And if we scroll down a bit, we'll find this thing. So we have something that we've tried to implement, a concept that we've tried to implement, and we have an idea of how it worked, but in the code it's not quite overlapping with what we thought. There's some overlap, but there's also these things outside. So what's going on? And I found a similar interpretation of this from a book from 2003. And this is from a book called How to Break Software Security by Whitaker and Thompson, so you have the intended functionality on the left, and then you have the actual functionality on the right. And in the middle, the green, that's the stuff that's working as intended. On the left, you have traditional bugs. That's things that were supposed to work but doesn't work. And on the right, in red, you have things that works but were not supposed to work. So basically, most of the time that would be security issues. So let's dive into an example. First of all, we tend to use strings a lot. So maybe we're using Java or using C#, and we have a strongly typed language, but we're basically writing stuff as though it was stringly typed rather than strongly typed. So it could mean implementing something like this. So we're going to register a user, and we get string email address, string password, string phone number. So string, string, string. But if we look at like the total amount of strings that are out there, and then the sets of email addresses and the sets of valid phone numbers, they're not the same, right? Well, maybe it was a SIP number, then maybe there was some overlap, but like for normal mobile phone numbers and normal emails, there is no overlap. And still in our code, we said both of them are strings. They're the same. And string is a weird concept. A string can be empty. It can be 2 gigabytes. Our email address is 2 gigabytes. I hope they're not. So what can we do? Well, we could use proper objects. And in the first version here with string string, we could accidentally flip the password and phone number. In the second version here, if we did that, we would get a compilation error. I love compilation errors. I mentioned this. We could even do better. We could stick it all in an object that has these fields and just wrap it up. Then we can do other things with it. But let's go back to these in the center for a minute, like email address, password, and phone number. What are these things? And Danberg Jonsson and the others in their book, they call them domain primitives. So they are basically something that wraps a value. So it wraps an email address string, but then enforces rules, it enforces invariance on that data. So it makes an implicit concept a string with assumptions. It makes an implicit concept explicit. So let's do an example in Java. So we have a class called phone number. That phone number takes a string, and then it sets that, it keeps that value in a local variable. So first of all, what we could do is we don't need to have getters and setters that you do typically in Java if we want this to be an immutable class. So we could just have one simple field that says final string value, this is the value that we're hoarding, and then we can enforce some rules on that. So if the phone number given to create this object is actually invalid, we'll throw an exception. So whenever you have a instance of a phone number object, you know that the data inside of it has been validated. You can't have a phone number object with an invalid value because it's checked in the constructor. In this case, we've used a static method to do this because then we can also ask the object up front, is this going to be valid or not? So we don't have to always throw an exception if we just want to check the value. That can be annoying. So that's just a sort of a convenience thing. If we do this, we also have to implement equals and hash code so that like hash tables and stuff like that would work properly. But we can also add more. So it just doesn't have to be this simple object that all it does is hoard this value and keep that. We can have other logic in this as well. So we can have stuff for a phone number. We can maybe have get country code or get local prefix or stuff like that. So we can add more stuff. It doesn't have to just be a stupid object that holds a specific data. If we move to more modern Java, we could use Java records. And in Java records, we don't have to implement hash code and equals because they are auto-implemented. And we also see that the syntax is quite a lot shorter. So in this case, we have the constructor argument is basically as a part of the first line string value, or here shown as 2 lines, but it's a part of the sort of the declaration. And there's no need to assign the value later in the constructor. We just check that it's valid and throw an exception. Java records are always immutable, meaning the value of the value field here, it can never be changed once a record is created. So if we want a different phone number in there, we would have to create a new object. And this is often a very good idea, because how else can we enforce the rules that are happening? It's easy for an object like this. It gets harder when the objects become more complex. So the nice thing about immutability is we know whenever something changes, it always goes through the constructor. That's the only place where things can change, so we always enforce the rules. And we don't have any weird code somewhere that goes in and that modifies a field randomly and then something else fails and it's super hard to debug. So this actually simplifies code. It's going to sound like it makes code harder to write, but it actually simplifies code later. But instead of using Java, we could move to Kotlin. And I've built some systems on this using these patterns and worked on them for several years. And in this case, we could use Kotlin, and then we could use some functional constructs. So again, it looks kind of like a record. We have the value as a part of the beginning here. We have a simple constructor that says, okay, this value must satisfy some checks. This is stuff that you can implement yourself. And the checks can be a list like this. So it needs to have a length between 8 and 20, and it needs to match a certain regex, for instance. So we can just create these convenience methods so we can reuse them across different domain primitives. And then we can use these functional constructs. So instead of throwing an exception in this case, we will run through the list of checks, and then we will return what we call an either. So an either is either something or something else. It means it contains either this type of thing, which in this case is a validation error, or it contains a phone number. And we can later check if it's one or the other. And the nice thing about this, if we compare it to exceptions, is we don't have to sort of catch it and do weird stuff with it. We can just check the return value and check what it is. And the super nice thing about that is we can actually we can get many of these. So if a user sends a complex object in, and we want to return not just the first field that fails, but all the fields that fails, this makes it a lot easier to do that. You can do it with exception as well, but it keeps getting more ugly. And then we could also have this is a valid method that we had in the Java version. So in Kotlin, we don't have static methods in the same way as in Java. We have what's called a companion object, which basically is the closest thing you get. So it's a part of the class that has some functionality. So basically static. Another example is a password class. So in this case, we have a password class that wraps a password value, and we want to make sure that that value is harder to get to. We don't want it to accidentally be printed in logs and stuff if someone prints an object and then that password object was randomly there. So in this case, we override the toString function to just return stars. So if anyone that tries to print this object, they're just going to get stars in the string where they're printing it. And then we can provide a different function for actually getting to the value. And we could even enforce rules on that. We can say you can only fetch this value 3 times, and then I'm going to throw an exception, or 1 time, and then I'm going to throw an exception to make sure that this value isn't read in many different places in the code. Some of the validations that we've talked about now cannot be enforced in the primitives. So one example, email must be unique. This is super hard to test for within one class because you probably want to talk to the database. Similarly, if we want to check if a phone number is a mobile phone number, that's also super hard to check for because different countries have so many different rules of what numbers are mobile number and what are like normal wired phone numbers. So there's even a separate library for this from Google for looking this up. And then passwords. Maybe we have some rules that says the password must not contain the user's email or phone number, the password must not contain the user's names, and it must not contain a password that's commonly used in breaches. Again, it's super hard for a single primitive to enforce these rules because it doesn't know, the password class doesn't know about the email or the phone number. But this is where this user registration object comes in. So instead of having them sent in one by one, we wrap them in a bigger entity, and that entity can then enforce things that go across these different primitives. So in this case, we can have a list that says the password must not contain the value of the email. The password must not contain the phone number value. And we loop through the names, and then we say the password must not contain any of these. So this is how we can enforce rules that go across different fields of this bigger object. But then we talked about password from breaches. How do we do that? So we could have a store function where we're actually going to store the password. And in this case, we have a username, and we have a new type called validated password. So not just password anymore, but validated password. How do we get a validated password? Well, we have a service, a password validator function. So this is more of a domain validation kind of thing, where we can ask, I have this password, can you check if this can be validated? And then it can, maybe this class has this list of commonly used password in breaches, or doing all kinds of other checks, and then returns a validated password or an error if it fails. So similar to it's still using the either, the functional aspect here, but it's more of a service rather than a simple primitive. So domain primitives, they can enforce simple syntax and semantics, but then we move to these bigger objects, then we can enforce rules that go across. Moving along and kind of moving back to the diagram we had earlier. So we have the database, we have the server side, and in this diagram I just collapsed the two on the left, sorry, into one, and says this is a client. This is it could be a REST client, or it could be like an HTML page in a browser. It could be anything. So let's say we have some data in our database, 2 fields, and we read that out, the user asks for something, we read that out, and we send it over to the user. Works as intended. And then a couple of years later, we're adding this new field. And this field is, let's say it's a credit score. It's not something we want to expose to the user, but because we've done something stupid and directly exposed our objects on the server to the client, this new field just flows through because we just exposed everything. And there are a lot of frameworks that kind of encourage this type of programming, which I really don't like, because you're gonna end up leaking data. And it can get worse than that. So let's say in this case we have a client that would normally send 2 fields. And let's say if it's a UI, this field isn't mentioned. If it's like in the API documentation, this new field that we added, it isn't even mentioned. So a normal client would just send 2 fields. These would be copied over to the server-side object and then stored back to the database. And things work as intended. But what happens then if the user would actually add this extra field? Well, again, because we're exposing our internal model, we might actually end up copying that data over as long as it has the right name, and then allowing the user to overwrite something that was intended to be read-only. And I'll give you an example of this. So this is a guy called Egor Homakov. Now, Egor Homakov, he created a GitHub issue that was 1,001 years into the future. How did Egor do that? Well, Egor, he figured out that when you were editing a issue that you created on GitHub, there was a timestamp called created at, which is typical for Ruby on Rails. That was also sent back and forth when he was editing the post. So he just modified that and sent it in, and then his issue was suddenly 1,001 years into the future. Now, if you go and look at it today, they've kind of modified it back. But the reason why he did this was he wanted to prove that in Ruby on Rails, it's super hard to get this stuff right, because the framework itself encourages creating a domain model from a database and exposing it directly through the API. And if you want to block something from being edited, you have to kind of deny list that. Instead of allow listing the stuff that can be changed, you have to deny list the fields that you don't want to change. And he was trying to prove that this is a bad idea. And in this issue on GitHub, people were like laughing and saying, haha, this is funny, you created a fun issue, blah, 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 but they didn't really care. But then he used the same bug to add his own SSH key to the GitHub Ruby on Rails repo. Then he got some attention. First he was kicked off of GitHub, but then they realized he only did this to prove that this was dangerous. And then actually in Rails 4, they changed the way that the framework works to make it easier to get it right. But I think this kind of way of writing code where we're directly exposing our internal model to the clients is a rather stupid one. So what I like instead is, and here you see the domain-driven security naming pop in, anti-corruption layer, using data transfer objects, using a contract instead of directly exposing our internal objects. So what this would look like is, again, we have these internal data, we read it into a server-side object, and then we copy it over to a specific object that's only intended for the communication, so a data transfer object. This new object doesn't have the new field that we added that was intended to be secret. So it's never going to be exposed to the client. Similarly, when we get data in, even if the client tries to add this extra field that they're not supposed to be able to edit, like the created at for Egor Homakov, our data transfer object, it doesn't really have this field. So there's nowhere to copy it. So this is a bit of an issue, you could say, okay, because now we're kind of washing the data that we're getting in instead of rejecting it. And this is a design choice. You can either say to your serializer that if you get an extra field that you don't like, you throw an error. Or you can just allow it as shown here. So in this case, we're just copying in the 2 fields that we want and then storing it back in the database. So now we've avoided a whole load of things. What this also allows us to do is we can modify, on the server side here, we can modify the internal model over here as much as we want. So these things can be modified without changing this one. So we can do whatever we want as part of refactoring internally without modifying the API and accidentally breaking our clients, which is quite nice. Here's an example of DTOs. So on the top you see a JSON. The JSON is an order with an ID, and then it has some order lines or some items where each of them have a product ID and a quantity. So the way, these DTOs, we use the primitive types like string and int and all those kinds of things, because these are just intended to assist us in transferring data back and forth. So these don't have to enforce the invariants. And what we can do then is we can give these DTOs also some more responsibility. We can tell them, you have a function where you can convert yourself into a proper domain object. So we give them the responsibility of knowing how to go from this data transfer object and into a proper domain object, which again would fail if there was some invalid data. So they work as a way for our serializer or API to transfer data back and forth, but then they can also help us get to the proper objects. And similarly for the order line. So now we have some nice objects that help us go back and forth, but they also help us moving from the representation that's on the wire and into proper domain objects. We don't have to write all of these classes specifically for each thing, but this is a really nice way of having specific object types per ID, but not having to do a lot of implementation to do it. So this is again Kotlin. So we have a wrapped UID. This could be the product ID and order ID, right? And then we have these two implementations of it. And now we're going to get help from the IDE. We're going to get compilation error if we try to put in an order ID where a product ID is supposed to go. And this has helped me a lot when I was writing code. And it also even helped us find a bug in an old piece of code, because we had this old code base that we got responsibility of. And we introduced slowly these concepts of domain primitives and ended up where a place where, hey, there's an ID coming in, but it's a product ID, but it's looked up as an order ID in the database. So this is obviously wrong. That was a bug that had been in there for a really long time. So we taught our DTO objects how to go to domain, but we can also allow them the opposite. So we can also say that this object has some static methods that go from the domain objects and to the DTO objects. So they know both directions basically, which is also quite nice, because then that simplifies the code where we're using these objects. We can just call to domain, and then we use from domain when we're going back. I mentioned immutability. So for an order, which wraps these things, this is the domain object, not the DTO object. If we wanted to add a new order line to this, it would have to return a new version of an order where this order line has been added. And again, maybe we want to enforce the quantity not just on each of these lines, but we want to enforce it on the order in total. So you can order 50 of one book and 50 of another, but you can't order 200 of one and 200 of the other, or even 150 of one and 100 of another, because that exceeds 200, and we don't want to send more than 200 items. So again, you can see we force this to go through our validation logic every time we try to change something. We don't have these setters and getters that allow us to directly access stuff and modify things. And a final benefit of going in this direction is also we can have some really clean controller methods. So these are the methods that are in our REST API. So often when I'm reviewing code, I see these methods have lots of different stuff. They're like ifs and def and all kinds of validations and all kinds of stuff. And it's super hard to read them. But in this case, what we want to do is we get in a DTO, we tell it to map itself over to domain objects, then we call the correct processing methods, and then we map the results back to an HTTP response. So all this method is responsible for is knowing how to get back and forth from a DTO to the domain object, and then calling the right processing method, which greatly simplifies stuff. But now I talked a lot about server-side code. What about client-side code, or even using TypeScript in Node.js on a server? TypeScript is kind of an odd beast. So we could try to use something similar. So we could add these super nice classes where we have a read-only value, so they're immutable. We have added some nice little validation rules there, and then we try to use it, and everything works as intended. So we have this, we create a username, we create a password, we want this register function where we can take the two of them, and we try to register with username and password, and that compiles, yes. But then we swap them, and it also compiles. That's not what we wanted. We wanted it to fail. We wanted a compilation error. But yeah, this is duck typing in TypeScript. So TypeScript doesn't actually look at the classes necessarily themselves. It looks at what do they actually contain. So because they both are just two objects that wrap something called value, that's what TypeScript sees. It sees value string, an object with a value string, and an object with a value string, and they have names called username and password, but they're basically two very similar objects. So in fact, we could just pass something like this and it would still compile. So we basically bypassed all the checks. We didn't get the compile time error that we hoped for. We could do something that's rather ugly. We could add these private fields, and this actually makes it fail during compilation time, but I don't like it, because why do we have this I thing? What does it mean? It does help TypeScript see that these are different objects, but it doesn't really look great. So, of course, there's a better approach, and that's to wrap it in an entity. So instead of passing string or value or whatever, we put it in a proper object, and then we use that in the rest of the code. So we actually know that we're passing the right object. Now, input validation in TypeScript, there is a super nice library called SOD. It has all kinds of features for creating these chained validators. So in this case, we have a parser where we see it's going to take an email and a password, and both of them are going to be strings. One of them is going to be minimum length of 10, maximum length of 60, and it's going to match some kind of email regex. And the other one is going to be a password, and it's going to have a minimum length of 8 and a maximum length of 256, like really simple logic here. But the nice thing by using this library, which you don't get from any other libraries, is you don't have to maintain a type in TypeScript and a parser. You can combine them. So now I can actually ask SOD to just create the type for me, and it will magically create the type where both of these are strings. So when I pass this object around later, I have a proper type for it. And it even has some similar semantics to this either thing that I showed you earlier. So we have a function called parse, which will throw an error. But we also have a function called saveParse. And what saveParse does is it returns an either. So it either returns something that has success set to false or doesn't have success, which means it failed to parse it, or it returns an object with .data where we can get the data that was parsed. So it's very similar to the either. It returns either something that's failed, or it returns something that is correct. But back to this blog post that I wrote. This is kind of the problem. So it's easy to validate some stuff, but it gets harder once these names contain things that can be used in attacks, like the quote character in Conan O'Brien. And to kind of prove this, there's this fun little Twitter message from way back in the day from, I think it's a Dutch guy. And he was attending a conference trying to register on the conference Wi-Fi. And then he got a SQL injection because, of course, he has this quote in his name, and they had implemented this the wrong way. And this is his name, so he needs to be allowed to have that name. We can't say your name is invalid because you're attacking our system. No, that is his actual name, so he needs to be allowed to have that name. So that's why I kind of said that input validation is not enough to stop cross-site scripting and SQL injection. So it can still help us get good data quality, and it can stop attacks, but we need to do other stuff as well. We need to make data stay data and not affect the way our code flows. Before I mentioned some examples of how to do this, I've seen a lot of places where people try to kind of get data, do some input validation, and then they try to be smart and add some encoding stuff while they're doing input validation. And that's not a good choice, because we don't know where that data will be used later on the way in. So encoding is something we do when we put data out somewhere. So we're going to send the data to a database, or we're going to send the data into HTML. That's where we can use encoding. But we're not supposed to do it on the way in, because we, as I said, we don't know. And maybe we did something wrong. Maybe we had the wrong encoding. And then now we have a lot of data in the database that's wrongly encoded, and we have to go back and fix it, which is super annoying. Typically, we can use some language constructs to help us with this. SQL injection, typically, we use parameterized queries. So we don't have to encode stuff ourselves. We use something that exists in the language already to help us avoid SQL injection. In newer frameworks like React and Vue and Angular, cross-site scripting mostly is gone because these frameworks handle it for us in a safe way. And other types of injection attacks, we need to escape or encode depending on where the data is going. And then I have to tell you a little story. So I was asked by some company to review some code. They'd hired some consultants to build a system for them. It was actually a web shop. And they asked me, hey, can you do a review of this store before we go online? And I thought, oh, you built your own store. That's brave, but okay, I'll review it. And so I started looking at it, and I quickly found that it was riddled with SQL injection, code similar to this. So just taking values directly from URLs, smacking them into strings, and then sending them to the database. And so I told them, yeah, you need to use prepared statements for this, so like to properly encode this. And this is what I kind of expected to get back, that they would like replace the data with question marks. They would then set the data as parameters and then execute the query. But what I got back was this. So they didn't do what I expected. They just basically switched the statement to a prepared statement, but then still did string concatenation, and then they were still just as vulnerable as they were before. And this was my fault, because I didn't tell them how to use it. I just said, use it. So I should have told them, so I should have given them an example and said, here is how you use prepared statements, but I didn't do that. So I felt a bit stupid after. But I also think they could have maybe Googled it to figure out how to use it. I don't know. But this kind of begs the question, can we do something with the APIs to kind of help us do this in a safer way? And the answer is, of course, yes, we can, and there are some good examples. One example is what's called trusted types, which now exists in our browsers. So a typical problem that occurs in web applications that aren't using modern frameworks is you get client-side cross-site scripting. So you're taking some data from a JSON somewhere and you're directly assigning it into inner HTML or similar places, and you get cross-site scripting. But even in a modern framework like React, we could end up getting cross-site scripting because in React they had this thing called dangerously set inner HTML. A super nice name for something because it's easy to look for when you're doing code review. But in this case, it's been wrapped inside a component. And so when you're using this component, you have to know that the body property, when you're using this component, is actually going to go directly into HTML. So it's dangerous to use the body property. And that's not visible when you're just using this component if you're not like inspecting it and seeing how it works internally. But trusted types is something we can tell the browsers to enable. So we can say content security policy enforce trusted types for script. And if we then try to take a string which contains an attack and just assign it to inner HTML, it's going to fail. It's going to say, well, I don't support getting assigned a string. I only support getting assigned a trusted HTML. Okay, so how do we get a trusted HTML? Well, we create a policy. And in a policy, we give it a name, and then we have this create HTML function that takes some data in the form of a string and then returns something that's a trusted HTML. And you can see on the bottom how you use it. You can say element assign inner HTML to, and then use the policy to create the HTML. But we don't have to do this ourselves. We can use a super good library called DOM Purify. And DOM Purify is by far the best XSS sanitizer that exists. So if you need to assign data coming from users, which you sometimes have to, if it's a blog post or if it's a CMS, then DOM Purify is your friend. And it can return trusted types, just if you add this argument at the end, return trusted type true. There's even another neat trick that I actually learned from Philip, who's organizing this thing, and that's the default policy. So if we create a default policy, it will automatically be applied if we try to assign a string. So we automatically sanitize data before it's sent in. This can be dangerous because, or not dangerous, but it can break the application if there's like a framework that's doing this and it's actually legitimately trying to insert HTML, and now it will be sanitized and it won't work anymore. But it's something that you might consider using if it's super hard to fix the rest of the application. Another example is a crypto library called Tink. So in Tink, they have they've looked at how crypto code is often written in Java, where everything is very generic. So it's not string, 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 but almost. And they created a new crypto library where actually things are well named, and you can't make the same mistakes as you can do in a normal when you're doing like normal crypto programming in Java and these other languages that it supports. And it has some really nice naming, just as React, like clear text, key handle, and insecure secret key access. Also makes it super easy to look through code and look for these things and look for places where users are trying to like circumvent the good ways of doing stuff. And then an example of where things failed. So in this example here, we have a little function called escape utils. And in this case, it's intended to take a list of bad characters at the top. So we're trying to take the double quotes, the single quote, and this like accented quote. And we're saying, well, we don't want them in our JavaScript. So it's intended to be used when we're going to put a string within a JavaScript string within an HTML page. The problem in this case is it doesn't escape the escape character. So we're trying to be smart and do like deny listing, but we should have used positive input validation instead. But in this case, we tried to be smart and use just escape the bad ones and then let everything else through. And we forgot one of the most important ones. And this was actually a bug in Ruby on Rails. I've been bashing on Ruby on Rails here, but they had this exact bug in their framework, so they actually did this mistake themselves. Another example where things don't necessarily work the way we expect if we don't know how the APIs work. So here's an example of a post request where we're sending in a username and a password, and then we try to look that up in MongoDB. There's a lot wrong with this code. Like we should never have like clear text password in MongoDB, but bear with me. So you can see it's sending in a username and a password, and it's taking those values, looking them up, and trying to figure out what's going on in the database and see if it has that user. The problem is if we write the data a bit differently with these angle brackets, it actually becomes an object server side instead of just a string. And in this case, we can do password greater than A. That's what the $GTE means. So you can imagine this makes it easy to kind of loop through things and find stuff. Again, we could have solved this with input validation if we checked that the password was indeed a string and not an object. But this was also a hard to detect bug if you don't know exactly what this URL argument parser did. Another example that keeps popping up is when we're parsing XML in Java, that keeps failing a lot because we have this concept of XML external entities, which are super dangerous. And I try to implement like parsers in Java and use safe XML parsing, and sometimes it just fails. So what I've ended up doing is I isolate the functionality for parsing, and then I like try to add the correct configuration so it doesn't allow these bad things. And then I add unit tests around, so I know that this configured parser will not do stupid things. So usually I add more than just one unit test. But then I know that I've done this correctly. So in this unit test, I've added an attack that hopefully should not work, and then I'm kind of checking that I'm getting the right error message back. And by doing this, we can make sure that we have like specifically configure things that are safe to use elsewhere. So maybe create a library that does this. So the generic advice is kind of isolate the logic and create like a reusable unit. And this is often smart to do if you're using an external library, you're just using like one function and you might want to replace it later. Then put it in a reusable unit. Make sure you configure it to work in a secure manner, and then add some unit tests for verification. So now we have something that's safe to use for everyone else in the team and maybe also across teams. So wrapping up, domain primitives. I keep getting some questions about this. Like, have you ever used them in a real project? Yes, I worked on a project for several years where we used this, and I love the compile time errors it gave me because it kept having my back when I did stupid things. So it's definitely something that I would recommend using. It must take a lot of time to create all those classes. Not really. The first ones take a bit of time because you set up like the validation rules and stuff, and then you can reuse validation rules and you can do all kinds of things. So over time, it doesn't take that much time. And also, it saves a lot of time later when I don't have to find all these stupid bugs that I introduced because I didn't have them. So I would actually say the opposite, that it will save me time. As I told you about the story where we found a bug in an old code base just because we introduced these domain primitives. And then the last one, what if we need to change the validation rules? And that's the tough one. So maybe you've done a lot of validation, you put a lot of data in your database, and then you realized, I made a mistake. I should not have allowed phone numbers starting with 999 because those are test numbers. Okay, so now I have to go through the database. But you would have to do that anyway if you had allowed those kinds of phone numbers. So it makes it a bit harder because if you change the validation rules and you have invalid data in your database, it's going to fail when you try to read that data because it tries to create the domain objects and then it fails. But you basically have that problem anyway if you have bad data. But it's a little bit more annoying. But you can write like scripts that go through the database during when you boot the application to figure out that stuff and maybe remove it or block those entries. So wrapping up, in conclusion, I think domain-driven security is a big help. We need input validation, encoding, escaping, and all those kinds of things. We can't just do input validation, and we shouldn't just do encoding and escaping, because like a username should not be 2 gigabytes, so we need input validation, and we need encoding and escaping to handle the cases where we have these quotes and things that are valid for the data, but that can cause trouble for us for security reasons. And then using domain-driven security, we know where to put that input validation. We can put that in these domain primitives, so we have a place for it. It's not randomly scattered across the code. This does help us get better data quality because we don't get all kinds of crap into the database. It's shielded off at the edge. We have this anti-corruption layer. And then, of course, that stops and hampers many types of attacks because we're just shielding off like large attack strings and all kinds of stuff that comes in. And it helps us get these compile time errors that helps us get better code and have fewer bugs. And that's it. So now we have some time for questions, if there are any. Nope.
Maybe I have a question actually. So you were saying about that we need input validation, right?
Yep.
But I'm quite confused because you also showed like some parts where you have that one name with the comma sign at above. How would you like solve that? That you use input validation, but you can also use these names, and you can also use the ones like script tag in a good context. Do you need like contextual input validation or something?
Or contextual output escaping or encoding. So you allow it to come in because it's valid, so the name is valid. So you'd have to allow the single quote as a part of the name and store it in the database. That's fine. But when you're doing the SQL query to store it, you have to make sure that you do that in a safe manner. And also when you, let's say you put it in a JavaScript string later, you have to make sure that single quote doesn't change the meaning of the what's happening in the browser. So then you have to use encoding or a framework, basically parameterize queries and use some modern framework like React. You're safe. But if you're, let's say you need to send it to a shell command for some reason, which I hope you never have to, but let's say you had to do that. Then you might have to use a different type of encoding because in a shell command there's lots of different characters that have meanings, like a $sign means start of an environment variable and all kinds of things. So then we need to use a different type of encoding and maybe think about it a bit differently. But at least if we know that the data can only contain these characters, like it can't contain a dollar because a dollar is never a part of a name unless you're like a US wrapper or something, then we can say, okay, I'm only going to allow like the single quote, and then I have to escape the single quote. I don't have to handle dollar signs or curly braces or all kinds of characters that might occur in that command, because I know what I have. But you could also say, I'm going to choose the safe option and encode everything that's not a letter or a number, because then I'm always safe, even if I change the validation rules later. But it's all about like contextual encoding for the target. Like, so if the target is HTML, I encode for HTML. If the target is SQL, I encode for SQL. But we can't block the person from having his name, right? Yeah. Good question. All right. Thank you all.